because of the screening effect or shielding effect of the D block elements, DR plus we are getting size edges. It is last class. I'm unmute చేస్తున్నా అందరినీ. సార్ అందరిని మ్యూట్ చేయండి సార్, అందరిని మ్యూట్ చేయండి సార్, సైలెన్స్ బాగా వస్తుంది. Right. I'm continuing, sir. So yesterday I discussed about atomic radius. This is the order of atomic radius. Scandium is highest size, nickel is smallest size, and copper and zinc increase in the size. This is due to interelectron repulsions between the d orbitals, electrons of d orbitals. Due to that, there is expansion of the electron cloud. Due to that, the size will be increased. So today I am going to discuss the remaining factors, first starting with the ionization potential, 1, electronegativity, electropositivity, electron affinity, just these values. After that, special properties, that is characteristic properties of the D block elements, such as catalytic property, complex formation, color properties, etc. I will discuss one by one. So here, all of you know very well, ionization potential I am discussing. Ionization potential is directly proportional to, and that is called, ionization potential is more whenever size is less, inverse proportional to the size. That is, ionization potential of a element inverse proportional to size or radius. At the same time, it also depends upon the number. It is point number 1. IP, it depends on electronic configuration. Depends on electronic configuration. All of you know very well the size of the size of the atoms of D block elements. Just before we will discuss. According to that, the size regularly decreasing like this. According to size effect, scandium should have the less IP value. Nickel must have the more IP value according to the size. That is, scandium is large size is more, nucleus attraction is less, then electron will be easily removed from the valency shell. Hence, scandium should have the less amount of ionization potential value, and nickel must have high amount of ionization potential value because its size is 1.15 radius. It is having the 1.44. It is on the 1.28. It is 1.17. Everyone can expect that according to sizes, if you go, ionization potential of a nickel must be more. But ionization potential of the nickel, here copper and zinc. So regularly the ionization potential increases in a period. Ionization potential increases in this transition period, transitional period, that is called 3D series, regularly increases irrespective of the size. This is due to, as size decreases here, what happens? Size decrease means electronegativity, ionization potential must be increased. I am writing both here. It is size, it is ionization potential. Ionization potential slowly increases because size decreases slowly. The electron configuration is similar. This is NS2 N minus 1 into D124 up to scandium up to chromium. But in chromium, electron configuration is 4s1. 4s1. That's why a small decrease in the chromium ionization potential value, followed by the atomic size are not almost same, but the electron ionization potential increases slowly. A doubt will arise. Size and IP inversely proportional to each other. When size is constant, why not ionization potential is constant? But not like that, because here 26 protons, 25 protons, 26 in iron, 27 cobalt, 28 in nickel. As protons increases, attraction force increases and size small decrease. Attraction force increasing even though size is almost constant. Hence, ionization potential increases. And in 1.17 size increased here. But even though size increase, here electron ionization potential may not be decreased. And here continuously it is increasing. Yeah, and it is also 4s1. 4s1 3d10. Everyone expect that 4s1 is unstable configuration. The ionization potential value must be less when compared with the nickel and zinc, because unstable configuration we can easily remove the electron with the field, but here the electron configuration may not affect here due to some other reasons, many reasons, and size increase here, electron ionization potential also increase. Zinc has more electron ionization potential because it is 3d10, 4s2 stable configuration. Because of stable configuration, it has more IP values. Here, again, I am confirming that ionization potential value depends upon these 2 points. One is size. Size is small, ionization potential value will be more. Second point is electron configuration. When the electron configuration is stable, its IP value will be more compared with the unstable configuration. For example, nitrogen 2s2 2p3, carbon 2s2 2p2, oxygen 2s2 2p4. Out of carbon, nitrogen, oxygen is small size, carbon is large size, nitrogen is medium size. Even though nitrogen has more IP value than the oxygen and carbon due to its stable electronic configuration. That is, nitrogen has more followed by the oxygen, followed by the carbon, it is ionization potential 1 value because it has stable configuration. To remove the electron from the stable configuration, somewhat energy is required more. It is unstable configuration, easily can be removed. So like that, here nitrogen has more ionization potential value than the oxygen and carbon because of, even though its size is medium between these two, its ionization potential value will be more because of the electron configuration, that is stable configuration. To remove the electron from the stable configuration, somewhat difficulty, hence ionization potential value will be increased. But in case of our case, in all these 2 types of configuration is there, 4s is a 4s2 3d 129. Sometimes 4s1 will be there. In case of chromium, in case of copper, we are having the 4s1 and 4s1. Here unstable configuration is there, even though ionization potential values are increasing. And forget about that here, about the electron configuration. Only based on the atomic radius we can explain the ionization potential of these compounds. And as usually in a group, what happens? As usually in a group, what happens? In a group, as size increases, for example, it is scandium, yttrium, lanthanum, one more is actinium. As size increases, IP value must be decreased. IP will be decreasing. But in case of titanium, zirconium, hafnium, Titanium has some titanium to hafnium, zirconium size increase. Zirconium to hafnium also size increase. Size is same. These two are size is same. Yesterday we discussed. Hence, hafnium, zirconium to hafnium, the hafnium has highest ionization potential value rather than decrease. Here, increasing takes place. Why? Titanium small size, more attraction power, hence electrons attracted hold by the nucleus strongly. To remove some X energy is required, but here size is increased. Size increased means electron will be easily removed, hence IP value should decrease. From here to here, what happened? Size is same. Size is same means IP value should same, but not here like that because size same, but here only 40 protons, here 72 protons. This attraction power is more here, hence removal of electron from here is very difficulty. Hence, hafnium has highest energy potential value than the zirconium and as well as titanium. So actually in a group, what should happen? Ionization potential value should decrease. 1 minute. Hmm. So right. So this is about this. Hence, ionization potential value of 4D and 5D series. If you compare, always 5D elements are either more ionization potential value than the 4D. Keep in the mind. Keep in the mind. There are two exemptions here. Even though unstable electron configuration there, chromium and copper, the ionization potential value is not affected. And here is a group. Actually, size increases, IP should decrease. But here what happens? Even though size increased, ionization potential value also increased. This is because of lanthanide contraction. It is the effect of post lanthanide contraction. About the ionization potential value. If anyone can any doubt is there, you can type the question. I can answer. Now coming to the electronegativity. Coming to the electronegativity. So according to the what is electronegativity? All of you know very well definition. The attraction power of the electron pair which is bonded between the two atoms. Two atoms are bond each other. The pair of electrons attracted by one molecule, one atom. This power is called this power of us. The tendency is called. It's a tendency. It is not it are not units. Don't have any units. Just tendency to attract the electrons of paired. So such phenomenon is called electronegativity. Electronegativity purely depends upon the size of the atoms. Irrespective of the electron configuration, everything. Forget all these. Only size, atomic radius is most important to explain the electronegativity of the, to predict the electronegativity of the elements. All of you know very well which is more size, which is less size. If you know the size, automatically we can say the electronegativity, which is more electronegative, which is less electronegative. So very, very easy. Here, for example, I am writing here nickel, palladium, platinum. Arrange the electronegativity order. Means what you have to write? Nickel is more electronegative because it's small size, and followed by the platinum, followed by the palladium. It is the electronegativity order. Anyone can say that why it is like this? Nickel is small size. Okay. Next, palladium is large size. Platinum almost same size. Because of small size and 3D electrons, less shielding effect. Here what happens here in this case, it is having some X, electronegativity is somewhat X, for example. In this case, size increased. Size increase means nucleus power decreases. The distance between the nucleus to valence shell increases, attraction power decreases, and electronegativity decreases, and here also should decrease. But these two are having the same size. This is difference between this is 32. It is, I think 78. It is 46. 46 protons are attracting the electron cloud. Here 78 protons are attracting the electron cloud, but size is same. Hence, same lanthanide contraction, will give the a leading that is platinum has more electronegativity than the palladium. Similarly, yesterday given boron, sorry, gallium, indium, thallium. Already, I think third group is over to you. In that, thallium has more electronegativity than the indium, followed by the gallium. Sorry, gallium followed by the indium. Why thallium has more electronegativity? Because of lanthanide contraction, it is 1.55 size. Size is 1.55 yesterday given. 1.24. As size is small, more electronegativity, and size is large. Out of these two, thallium has almost equal size, but the 32 products are extra because of electronegativity. It depends upon the only nucleus power, that is atomic radius and nucleus power. Atomic radius is small, electronegativity will be more, but any two atoms have the same size, then you have to think about the electronegativity depends upon the its nuclear force. For example, zirconium, hafnium are the equal in size due to lanthanide contraction. But hafnium has more electronegativity. This is due to it has 32 protons are extra, that is magnetic force, attraction force is more, hence it can easily attract the electrons or ligands, etc. Hence they are going to form stable complexes, coordination complexes when compared to this one, or stable binary compounds. Either binary compounds or whatever the compounds are more stable when compared with the zirconium and hafnium. Like that, once you know the size of the atomic radius or size of the atoms properly, you can explain the many things. So now anyone can post your doubts even the tomorrow also directly to my WhatsApp. I can give answers. Third one, electropositivity. It's very simple. Electropositivity means the tendency of losing electrons. Losing electrons. It is completely reverse to the electronegativity. Complete reverse to electronegativity. That is when our size is more, electronegativity will be less and electropositivity will be more. So this is the same concept depends upon the sizes. So anyone tell me that zirconium and hafnium, which can have the more electropositivity? Manganese and iron, which can have the more electropositivity? Yeah, zirconium, very good. Because zirconium, hafnium has the more attraction power, it do not lose the electrons easily. Very good. Keep in the mind and followed by the remaining other properties. Now, somewhat time will be taken to explain this. I will go to the first density, which is density, more density metal, and second one metallic character, metallic nature. Density and metallic nature is most important points in the examination. How the questions will come, etc. I will explain. So first density. What is density? Yesterday I given. Density is equal to mass by volume. Mass is more, volume is less, then density will be more. Now tell me that zirconium and hafnium, which has more density? Zirconium and hafnium, which is more density? Type answers. Yeah, hafnium. Why? Why? Zirconium has 40 protons and 40 neutrons. Size is same. And here also it is having 72 protons plus 72 neutrons approximately. I can give the double. Yeah. Here what happens? Size is same. Denominator is more, numerator is same. హారము సమానంగా ఉంది, లవము ఎక్కువగా ఉంది. అప్పుడు ఏమైతుంది? ఆటోమేటిక్ ఇట్ హ్యాస్ మోర్ డెన్సిటీ దాన్ దిస్. Keep in the mind, always density increase in a group. Density increase in a group and as well as in a period. It is a very, very important concept. In a period, density increase, in a group also increase. But sometimes density will alter because of the radius effect. For example, I am going to give the one boron, aluminium, gallium. What is happening here? Boron is having the 8 protons, 8 electrons. Size is 0.8. It is 13 protons, 13 neutrons. Size is 1.24. Here 31 protons plus 31 neutrons by size is 1.23. Small size. Then what happens here? Gallium has more density. Gallium has more density. Suddenly density increases. Then indium. Indium has, what is that? 49 plus 49 by 1.5. And coming to the thallium, it is having the, how much thallium? Thallium is having 81 protons plus 81. Approximately, number of neutrons will be more. It is 1.55. See here, 1.5, 1.55. Just 0.05. Very small increase. Hence, what happening here? Thallium has highest density in the periodic table, in this group. And suddenly, aluminium to gallium, suddenly density increase. Boron to aluminium, density not increased. It is lighter element because here 18 and 16 and 24, size increase more. Here 0.8 to 0.4 size increase, but mass increase very small. Mass increase very small, but size increased more. Here density is not going to increase more. But here the year mass increased more, size almost same, rather than decrease, somewhat decreased. Hence here density of gallium is highly increased, almost double, almost double. So keep in mind that density is a matter of mass by volume. It is a ratio between the mass by volume. Now, all of you know the masses, atomic weights of the elements, that is atomic number plus atomic number divided by the volume. Volume means size. Size. So all you know that it now periodic table, in the periodic table, 3D elements, 4D elements, 5D elements, their sizes. You can go to the JDL book, and in that all atomic radius are given, all densities are given. You can compare. Otherwise, according to your knowledge, you also can take that one, and densities can be easily predicted. And the most important point in the case of density, I'm going to explain now. What is that most important? So listen to me carefully. Here, one, it is the size of the ball. Next, it is 4D series. Next, it is 5D series. Yesterday I given the sizes. Yesterday I given sizes. Listen to me carefully. Here, volume is, size is decreasing, mass is increasing. 21 protons, 22, 23, 24, 25, 26, 27, 28. Here 28. Slowly atomic radius is decreasing. Atomic radius is decreasing. Mass increasing. Hence density must be increased. Size decreasing. Mass increasing. That is numerator increasing. Denominator decreasing, numerator increasing. Overall, the ratio D is equal to increasing. Up to here, even though here size constant, mass increasing, and after that, in copper and zinc, even though mass increase 29, 30, size also increase. Mass increase as well as size increase. Hence, the ratio somewhat decreases, and copper and zinc are lighter elements, less dense elements than the nickel, palladium, all these elements. When compared to these three, four elements, cobalt, nickel, iron, cobalt, nickel, copper, zinc has a less density. And from top to the bottom like this. And in a group, what happened? In a group, because of Lagrange contraction, finally here, zirconium to hafnium suddenly increases. Here manganese, technetium to radium, here palladium to nickel, palladium, platinum. Suddenly increased here density because of laser contrast. And because of this D block elements, the D block elements can effect here also over density. Because of interrupter depression, size increase here, their density decreases. Because of the d electrons shielding effect as well as lantern contraction, these elements are cobalt, nickel, iron, cobalt, nickel. These are eighth group. Possess more density in the periodic table. Possess more density in the periodic table. Actually, left to right, density increases. Top to the bottom also increases. The top to the bottom increase of the density more suddenly increases in the 4D to 5D because of lanthanide contraction. From left to right, as size decreases, mass increases, density increases. But here, size unexpectedly increased because of the d electrons, interelectron repulsions. Due to that, somewhat density decreases. Hence, finally, these elements are having the most density elements in the periodic table. Hence, in the periodic table, iron, ruthenium, osmium, cobalt, rhodium, iridium. These two elements are osmium and iridium almost equal. These are among the highest density elements. Highest density elements, it is 22 grams per cc. 1 cubic centimeter area possesses 22 grams weight. This size of volleyball size has 360 kgs. Volleyball size or less than that one has 360 kgs of the weight because of iridium and osmium are the most important elements. They are highly density elements. And compared with the 3 to 4 times greater than the iron. So this is about the density. Any queries you can type now. About the density, any doubts, any clarifications, you can doubt or you can ask by unmuting yourself, anyone. If you know, I will continue. Okay. I agree that you may not have the doubts. You don't have the doubts. Even if you have any doubts, you can post in the WhatsApp directly to me. I will answer in the next class. Now, coming to the metallic nature. Metallic nature. So it is a very interesting question. Tell me that iron, out of iron, copper, which is best metal? Type answer. Iron. Avanti iron. Iron. One. Who is the given copper answer? Yeah, iron. Yeah. Who is one person given copper? Again, type it. Who is that? No problem. Mistake will give the. Yeah, okay. Both are D block elements. Both are D block elements. But what I am asking you, out of iron and cobalt, iron and copper, which is more metallic in nature? Which is more metallic in nature? Who will give the answer, proper answer? Yeah, iron. Anyone say copper? Anyone say the copper? Voice Afshan, copper. Okay. Only one out of the answered one. Most of the given copper. Swati copper. Okay. Any other answers? Can you give the reason for why copper? Why not iron? Or why iron? Why not copper? You can unmute and answer. Standard reduction potentials. Okay. Any other? Because DD transition. No, no. Next, next, next. Any other answers? Why iron is copper has more conductivity. So, no, okay. Metallic nature, because of more metallic nature, it has more conductance. Okay. Any other answer? So, you have an idea, but not correct one, that idea. Your idea is not correct one. I'm going to explain why metallic nature. So, can you tell me that metallic nature in a period, what happens? Metallic nature in a period, what happens? What happens to the metallic nature in a period? Decreases. Okay. Decreases. In a group, Sai Kumar say increases. Okay. Any in a group, automatically decrease means increase, yes or not? Yeah. Tell me that. Tell me that. What is a metallic nature? Can you type anything? What is the meaning of metallic nature? What is meant by metal nature? Which is good metal? When we say one metal is good or best, do you have an idea? Don't worry, time will be there. I will continue up to examination. No problem. What is the metallic nature? Have more conductivity, more electropositive. Very good. Yeah, yeah. Next, any other answers? Reactivity and conductivity. Okay. Loss of electrons. Okay, I will continue. Listen to me. So metal nature means first of all, a good metal. A good metal possess. A good metal or best metal possess. You can note down possess one. Metallic shows luster. మెరుస్తుంది. Simple point. High electropositivity. Less electronegativity. Less electronegativity. Most important, malleable and ductile. No one give an answer this one. Malleable and ductile. It is most important point. Next, what is the malleability and ductility? Yeah, malleability and ductility. What is that? And sonorous. Sonorous means sounding. And luster shows sonorous. This is simple point. Malleable and ductile and possess electric conductivity. Electric conductivity. And conducts heat. Conducts heat. Conducts heat and electricity. That means high electropositivity means that is automatically more size. Lesser electronegativity means more size. Malleable and ductile possess electric conductivity and conducts heat and electricity. That's all. And most important, they are soft. Metals are soft, can be easily cut with knife. Knife. కత్తితో తేలిగ్గా పోయవచ్చు. Now, after this, tell me that copper, iron, copper. I'm writing scandium, iron, copper. Which is best metal? Which is best metal now after this? After listening, copper. Out of scandium and iron, give the order. First it is 1, it is 2, 3. Best metal is there. What is the best metal? Copper. What is the not bad metal? Which is bad metal? Scandium. Which is bad metal? Again, I'm asking. Best metal is copper. Bad metal is scandium. Okay. Okay. Now, 3, 2, 1. Okay. Now, listen to me, friends. Actually, best metal is copper. Bad metal is iron. Bad metal is iron, not the scandium. Listen to me. What I am telling you, it is very, very important. Not here only. What is metal actually you don't know. These are the properties shown by the metal. Out of lithium, sodium, we can easily cut with the knife. Sodium is the best metal. Lithium is not best metal. Cesium is the best metal because it has more electropositivity. I am going to first group first of all. In the first group, lithium to cesium. Cesium is the best metal. Lithium is the bad metal. But out of all these are good metals. From left to right, what happens? Lithium converted to magnesium, beryllium. Here valency increases. Because of increasing the valency, the attraction power between the two atoms increases, and they are become very hard. Metal nature decreases. If valency of an element, metal ion is more, its metallic bond is less, it is bad metal. Silver, copper, Rm, +1 only. Its valency. Hence they are best metals. Next followed by zinc and mercury +2. In case of iron, it is also +2, +3, but difference is they have unpaired electrons, the d orbitals, 3d4, 3d5, cobalt 3d6, manganese 3d5. But copper has 3d10, zinc has 3d10. The electron configuration of the d block elements which cause the badness in the metallic nature. Why the metals are, why this, what is actually, before going to learn this, what is the metallic nature? What is the metallic nature? What is the metallic bond? Yeah. Okay. Now, so I am going to explain now. It will be settled down because my signals may lose something. Now, I am going to explain now what is the metal now, what is the metallic nature. After that, you have to answer. Now, according to the electron pole theory, that is called Broad and Lorentz theory. Drude's and Lorentz theory, I think metallic bonding it is chapter. All of you know very well, the atomic bond, the bonding is several types. Ionic bond, covalent bond, and coordinate bond. Similarly, metallic bond. Metallic bond is not formed by the. Okay. I am enlarging. So signals may be affecting here somewhat. Take some time. It will adjustable. Okay, now, yeah. Now you are hearing. Okay, now how it is? Now how it is? Okay, done. Okay, now continuing. Okay, right. So, right. Sometimes signals are becoming bad. That's why you are not clearly seen. Now, according to Drude-Lorentz theory, metallic bond means, for example, lithium and lithium. It has only one electron. It has one electron, 2s1, 2s1. There is chemical bond, covalent bond, lithium. Lithium must be covalent molecule because Their size is S orbitals. One electron should overlap to form the bond. But lithium atoms are not going to give any chemical bond formation. No covalent bond. Lithium shows metallic bonding. It is a cubic type crystal. LA it is having the BCC or FCC such type of crystal structure. How it is forming, we don't know. Lithium has only one electron. One more lithium has one electron. How they are forming the bond? How if they share one electron each, we are going to get the lithium 2 molecule, like sodium 2 molecule. But here we are not getting as a divalent molecule. It is not diatomic molecule. Lithium is a crystal. Lithium is a solid. It is a cumulative combination of the lakhs of the crores of the molecules to give a solid. That means in this a different type of bond is there. It is lot of explanation is there here, but for sake of our convenience, I am explaining only few points. Sir, now it is okay. Now it is okay. Here signals are good. Afsan, just go outside somewhere. Here you having some. Okay. Okay now. So majority they are okay, but all right. Afsana, you say that okay? Okay. Now here what happens? So lakhs of the lithium atoms or sodium atoms release the electrons into the lithium plus n number of atoms release the electrons into lithium plus n electrons. The n electrons can form a pool of electrons. Pool of electrons. In this pool, lithium plus ions are embodied like this in a order. Here the plus ions attract the minus charge, that is electrons. Electrons attracting the plus and form a metal. Due to attraction, electrons do not go away and ions do not go away. They are like a crystal. If you are going to hammer it, they can be extended like a wire. They can make it like a plate, and all they are going to form like this, like this. Everywhere there is arrangement. They can withstand for the stress. దాని మీద ఒత్తిడి పెరిగి పలకలాగా మారిపోతున్న అరేంజ్మెంట్ ఉంటుంది. ఇప్పుడు మనము కష్టపడి వీటి మీద లైట్ పడగొడితే ఈ ఎలక్ట్రాన్స్ జంప్ అవుతాయి బయట. Cesium. It is used in the cesium is used in the photoelectric cell. Light will be produced. From the light, electricity will be produced. Solar lamps, solar panels. Here, what happening? There is a different type of bond between the ions and electrons. It is not a covalent. It is not ionic. It is a different type of bond called metallic bond. According to Drude-Lorentz theory, whatever the distributed electrons are from a pool or a cloud of electrons, in that the ions are going to embodied. Because of this one, electrons do not lose easily and ions do not go away. They are going to be packed at one place. It is a solid. Now, if you dragon this, it can be dragon. If you cut it like this, easily cut into two pieces. If you hammer it, they can set into sheet. But the same thing if we go with the magnesium. Magnesium +2. Here number of electrons are more, and magnesium +2 and electrons are having more attraction, strong attraction. Hence, somewhat this bond is strong, and whatever the crystal formed is very hard. Aluminium still hard. Why aluminium hard than the magnesium? Because aluminium small size +3 charge, it releases 3 electrons each, and in the pole 3 electrons attract the +3 charge. Attraction is more and more, and it is having very hard. That means, so lithium plus electron, 1 electron lithium, sodium plus 1 electron and sodium. As size increases, what happens? Attraction between the ion and electron decreases. Hence, the crystal structure that is called the strength of the crystal decreases, and cesium is very easy to cut, easy to spread, easy to drag into wire, easy to malleable, easy to ductile. It's more electricity. Easily excitation of electron takes place on irradiation of the light in the cesium. But it was tough in the lithium. So what I'm going to conclude here, metallic nature completely depends upon the valency of the electrons and electron pull. More number of electrons released by the metal atom, whatever the pull is with more electrons, the embodied ions and the electrons are attracted more, and crystals will be very hard. That is called, it's not easy to drag, not easy to malleable, not easy to ductile. Keep in the mind. So because of this, a best metal is easily cut with a knife. Opaque, having the sonorous, having the transparent, and at the same time, it has most important luster. So the luster, more luster is there, more luster. In according to the copper, silver, gold, what happening? Gold is more luster, copper is less lustering. Out of the iron, copper, iron is having the less luster. So by seeing the luster only, we can decide that a good metal or bad metal. So it is one of the important points. Now, I am coming to the point now. It will be useful to you. Dulles-Lorentz theory, valence bond theory, and MOD theory for metals. Their conductance is there, one chapter. You can read, it will be useful there. But I am going to discuss here why metallic nature decreases. Actually, metallic nature decreases in a period. Why? Lithium, plus and 1 electron. Beryllium, plus 2 and 2 electrons. Like the sodium, magnesium, aluminium. As left to right, what happening? As left to right, what happening? Atomic radius decreases, charge increases, number of electrons increases, attraction increases, pool of electrons are more, ions and electrons attract more and more, becomes very hard material. Hence, sodium easily we can take like a, that is called jaggery. బెల్లం మనం చుంచినట్టుగా సోడియం చుంచవచ్చు, మెగ్నీషియం చుంచలేము ఎందుకంటే కాకరవత్తులు కాల్చేటివి. ఎట్లా ఉంటుంది? అల్యూమినియం ఇంకా హార్డ్ ఉంటుంది. అల్యూమినియం వైర్స్ ఉంటాయి, అల్యూమినియం బౌల్స్ ఉంటాయి. మెగ్నీషియంతో చేసినవి అట్లా ఉండవు, కొంచెం మెత్తగా ఉంటాయి. అదే సోడియంతో చేస్తే విడిచిపడేయచ్చు సోడియంని. అండ్ మోర్ రియాక్టివ్. చూడండి, సోడియం is highly reactive, exposed to water, immediately burns. But magnesium do not burn. If you are going to make it flame, it's going to burn. Aluminium never burns. So shear, metallic nature. And sodium, బెల్లం లాగా మెరుస్తుంది, మెగ్నీషియం మెరుస్తుంది తక్కువ, కాకరవత్తి చూడండి. And but aluminium less lustering. As the left to right, atomic radius decreases, charge increases, number of electrons in the pool increases, its metallic nature decreases. And coming to our D block element now, the D block elements: potassium, calcium, scandium, titanium, vanadium, chromium, like this. Scandium 3d0 plus 3, titanium plus 3, 3d1, vanadium plus 3, 3d2, chromium plus 3, 3d3, Similarly, manganese plus 3 plus 2, 3d5, because it's plus 2 stable, and iron plus 2, 3d6, cobalt plus 2, 3d7, nickel plus 2, 3d8, copper plus 1, 3d10. Here says 3 electrons, pool, scandium, valence, core valence is like mercury, calcium. Here 1 electron, 2 electrons, 3 electrons. Here scandium forms only metallic bonding. Scandium forms only metallic bonding. Plus 3 electrons and scandium ions like before, like sodium and magnesium, aluminum. But titanium plus 3 and releases 3 electrons per cloud going to form metallic bond. The D1 of one metal ion, D1 of other metal ion are going to form the covalent bonding. D1 overlaps to give the covalent bonding. One covalent bond for the one atom. Here 2 covalent bonds. Here 3 covalent bonds. Here 5 covalent bonds. Here 4 covalent bonds. Here 3 covalent bonds. Here 2 covalent bonds. Here 0 covalent bonds. In copper also only metallic bonding, because d atoms having the 0 electrons, all are paired. In scandium, no electrons. Hence here scandium has only pure metallic bonding. Copper also having, zinc also having pure metallic bonding. But in between that, scandium, titanium, vanadium, slowly, along with the metallic bond, there is the covalent bonding. Covalent bonding between the titanium. All titaniums are going to form the one and each other covalent bond formation. That covalent bond formation is very high in the manganese and chromium and iron, cobalt. What happening here? Ante idanamata, not only metallic bond here, covalent bond like carbon hybridization, how they are going to form the graphite and diamond. Like that, the valency bond are going, for example, manganese 5 is there, D5, all these are going to form a covalent gained molecule. ఒకటి ఫామ్ చేసుకుంటూ డైమండ్ లాగా, గ్రాఫైట్ లాగా బంధాలు పెంచుకుంటూ పోతూ ఉంటాయి కోవలెంట్ బాండ్స్ అలాంగ్ విత్ ద మెటాలిక్ బాండ్. మెటాలిక్ బాండ్ ఉన్నందున అవి మెరుస్తాయి, ఎలక్ట్రిసిటీ కండక్ట్ చేస్తాయి, మెటల్ లాగా ప్రవర్తిస్తాయి. వాలెన్సీ బాండ్స్ ఉన్నందున అవి గట్టిగా ఉంటాయి, హార్డ్గా ఉంటాయి. అవి నో malleable, no ductile. Tungsten is a filament, very hard filament. Iron, hard material. On heating and on hammering only it will be malleable. Otherwise, it's not possible. But copper easily we can withdraw, right? And aram, gold. Make it sheets. Keep in the mind. So no, WhatsApp directly sent to me by my WhatsApp. No group. So now left to right, scandium to manganese. As number of d electrons increases, covalent bond formation increases, metallic bond increases. And when from manganese to nickel, covalent bond decreases, again metallic nature increases. And in the copper, convert into metallic nature, zinc metallic nature. Hence here, rather than behind our expectations, the metallic nature slowly decreases and increases in the copper and zinc, followed by again decreases. Hence, potassium, calcium is the best metals, scandium is not best metal, and iron, manganese are bad metals, cobalt, nickel also somewhat bad metals, and copper become good metal, zinc become good metal. Out of copper, zinc and copper, silver, gold is the best metals because they have only valency 1. Like potassium, lithium, they can easily cut with a knife, they can easily drag it into where they drag into sheets. And that's why copper is used in the electric wires, not the iron, not the aluminium in the home, household wiring. Because copper easily dragged into wires. Copper plates easily molded. And all of you know very well about the gold. Gold is a very, very, very precious, very best metal very noble metal. It can easily convert into any shape, any design, because it is malleable and ductile. So keep in the mind. So I think you have understood and you are going to give the answer properly in the examination, which is best metal out of these two. Now, any doubts here? Any doubts here? Density is over, metallization is over, electronegativity, electropositivity, and ionization potential, electron configuration, oxidation states, atomic radius, all these points are covered. If you have any doubt, you can type now. Otherwise, I will continue our characteristic properties such as magnetic properties, catalytic properties, complex formation ability, and color properties, etc. I will discuss one by one. I am waiting for your doubts. Within 1 minute, you can type or unmute and ask. No. So I am going to now continue magnetic properties first of all. Magnetic properties. So magnetism completely depends upon the. So which is paramagnetic, which is diamagnetic, which is paramagnetic? Magnetic properties. We are having the paramagnetic complexes, paramagnetic compounds, diamagnetic compounds, ferromagnetic, ferrimagnetic, antiferromagnetic. Okay. So these are 5 types of compounds are there. First of all, before going to answer this, all of you know very well paramagnetic. Whenever the atoms have unpaired electrons, they can show paramagnetism. Either completely paired or completely empty or diamagnetism. The electrons with more parallel spins are called ferromagnetic. Antiferromagnetic means number of parallel and antiparallel equal. Number of parallel and antiparallel equal. Antiferromagnetic, no magnetic moment, mu is 0. Ferromagnetic means when the uneven number of like this 3 are parallel, 3 are antiparallel, equal to only 1 electron is there. Excess. This will be cancelled and 1 will be there. It's called ferromagnetic. Okay. I will explain one by one. So you need that one. Okay. Okay. Voice is clear? Can I explain total completely? Can I start with the basics? ఏం చేయాలరా బోర్డు ఈ టైంలో ఒక్కోసారి థిక్నెస్ ఒకసారి బాగుండట్లేదు, అది నా ప్రాబ్లం. వర్షాలు చేయడం వల్ల మరి క్లియర్గా ఉందా ఇప్పుడు? చూడండి
రాయండి సరే, రాసి చూడండి.
ఆ 10 మంది పిల్లలు బాలే అంటున్నారు.
కొంచెం వాయిస్ కూడా డ్రాగ్ అవుతుంది. స్టార్టింగ్ బాగానే ఉండింది, మధ్యలో కొంచెం బ్లర్ అవుతుంది.
వీక్ అవుతున్నాయి సార్. ఓకేనా సార్? ఓకే. సో ఐఎమ్ గోయింగ్ టు ఎక్స్ప్లెయిన్ ద మ్యాగ్నెటిక్. హలో
సార్. సార్ క్యారీ ఆన్ సార్.
ఓకే. ఇది పోయింది సార్, అది ఏమంటారు, బ్లూటూత్ పోయింది సార్, అందుకని మాట నొస్తారు. హలో సార్ వినొస్తుందా?
ఫైన్ సార్, క్యారీ ఆన్. ఓకే, వినపడుతుంది సార్.
బ్లూటూత్ మధ్యలో ఆగిపోయింది సార్. ఓకే, రైట్. ఓకే, రైట్. So in case of magnetic properties, first of all, listen to me, how the magnetism will be produced. Sir, Bluetooth వినొస్తుంది. ఒక్క నిమిషం. హలో హలో సార్, హలో హలో హలో
సార్
బ్లూటూత్ ప్రాబ్లం వచ్చింది సార్. బ్లూటూత్ ప్రాబ్లం
వస్తుంది అని వాయిస్
సార్.
కొంచెం లో ఉంది, బట్ ఇట్స్ ఓకే, ఆడిబుల్.
అదే బ్లూటూత్ లో ప్రాబ్లం వచ్చిన అవ్వలేదు.
ఓకే సార్, ఇప్పుడైతే వినపడుతుంది.
చేంజ్ చేశాను సార్. రైట్.
ఓకే సార్.
So I am going to explain what is the magnetism first of all. Any revolving body, a charged body, any charged body is spinning on its own axis. A charged body spinning on its own axis exhibits magnetism. That is, they have south and north pole. They possess south and north pole. South pole and north pole. Any body which is spinning its own axis, it creates a magnetic field, possesses south and north pole. Here, electrons are having negative charge, rotating in a direction either clockwise or anti-clockwise. Hence, as the charged electrons spinning its own axis, hence they have magnetic momentum. So the magnetic field, they can generate magnetic field, south and north fields. They can behave as a tiny magnet. I am repeating, a charged body spinning its own axis can generate magnetic field that possess south and north poles. Here, electrons are having negative charge. They are going to spin towards own axis. It is called spin angular momentum. And also the electrons revolve around the nucleus. It is called as orbital angular momentum. That is, the magnetic field which is generated due to self-spinning of electron on its own axis is called as spin angular momentum. It is given by S. S plus of, S minus of. S plus of means it is having clockwise direction spinning on its own axis, and S minus of means it is rotating anti-clockwise direction on the axis around the nucleus on its own axis. And these electrons are going to revolve around the nucleus, and they are going to revolve around the its own axis. This is called S. This is going to move around the nucleus in orbit. This also have some momentum of magnetic field, that is called L. It is called orbital angular momentum. I am repeating. The magnetic momentum of an element or a compound is produced due to two types. Produced because of two types. One is electron spinning its own axis due to its electric charge and rotating. It can create a spinning magnetic field. This magnetic momentum is called spin angular momentum, S, denoted by the S. And the electron, this electron around its own axis as well, it is going to rotate around the nucleus in a orbit. The orbit also have some momentum, some magnetic moment. It is called orbital angular momentum. Totally, S plus L is the total orbital angular momentum. Very important here. S is angular momentum, that is magnetic momentum, which is produced by the tiny magnetic element electron due to spinning its own axis. L is the orbital angular momentum produced due to electron which is rotating around the nucleus in a orbit. The sum of this is called total magnetic momentum of that particular atom. Hence, for example, I am taking here anyone copper. I am taking the copper. Copper has the 29 is the atomic number, 3D10 4s1. In the copper, nucleus has 29 protons. It is 1s, 2s, 2p, like this. It is 3D, 4s. The electron here, one electron is going to rotate its own axis. It is called S, and it is rotating around revolving around the nucleus L. The S plus L is equal to total angular momentum, total magnetic momentum. Now, S is equal to, in case of 3D series, in case of 3D elements, starting from scandium to zinc, L is equal to almost 0. The contribution of orbital angular momentum of 3D elements is 0. L is 0. That is, due to orbital angular momentum, no magnetic momentum is produced. Whatever the magnetic momentum produced because of only electrons, that is spin angular momentum. This is due to small size of the atom. The d orbitals are very small size. But whenever, if you going down the group 4D, 5D, the d orbitals are very large in size. Due to large in size, they are try to pair up more. And because of pairing up, the orbital angular momentum is going to picturize. There, in case of 3D and 4D in the lanthanides and actinides, L plus S values are combinedly give the magnetic moment of the element. But in case of 3D series, because of small size of d orbitals, only S is working out, no L. L is equal to 0. Hence, in the examination, whenever they ask
what is the magnetic moment of below element means? In case of it is 3D series, that is scandium, titanium, vanadium, etc. Count down the unpair electrons and use the spin only formula, that is called root n into n plus 2 or root 4s into s plus 1 formula directly and write the what is the magnetic moment. But this formula is not useful to the spin only formula, not valid for the below element, that is 4D series and 5D series and lantern. There, even one electron may cause the more magnetic moment. Even the 5 electrons can give the less magnetic moment, depend upon the L and S value. Sometimes S values and L values are combined to each other. Sometimes because of pinching of earth angular momentum, L values are going to subtract from the S value. For example, I am going to repeat in the lanthanides. In the lanthanide, europium has 7 electrons, 7 electrons, but its magnetic moment is very less. Holmium, dysprosium have the only 4 electrons, but their magnetic momentum is about 10. 4 electrons give the 10 boromagnons. In case of europium, 7 electrons are there, but only can give the very less, almost 0 magnetic moment. So magnetic moment is depend upon number of electrons, spin only magnetic angular momentum, as well as earth angular momentum. But you have to apply the spin only formula for a 3D series, but this formula will not be applicable for the remaining all. Now, with this introduction of the what is the magnetic moment, how it will be generated, and how to calculate, etc., I will going to explain now. I am repeating, an electron is free. It is rotating its own axis, spinning on one axis can create the magnetic field. This magnetic field, if the electrons are paired up, what happens? One is rotates clockwise, one is rotates anti-clockwise, and this magnetic momentum opposite, and each other cancelled. Net magnetic moment is 0. That's why I am repeating. Electrons, unpaired electrons are going to rotate clockwise. All are rotate clockwise, what happens? Magnetic moment increases. For example, 4 electrons are there. 4 electrons are there. 4 unpaired electrons are there in the element. These 4 are rotating clockwise around its own axis. అన్ని కుడి వైపే తిరుగుతున్నాయి. ప్లస్ ఆఫ్ ప్లస్ ఆఫ్ ప్లస్ ఆఫ్ ప్లస్ ఆఫ్ టోటల్ ఎన్ని అవుతాయి? 2. Its magnetic moment is very high. It is called ferromagnetic in nature. But out of these 4, 2 are rotating clockwise, 2 are rotating anti-clockwise. What is happening now? These 2 are clockwise rotation. Its magnetic momentum is different. Both are opposite, but same value. Both will be cancelled. Net magnetic moment is 0. Even though they have 4 unpaired electrons. Yes, even though they have 4 unpaired electrons, 4 has magnetic momentum, but 2 are having the positive momentum, 2 are on the negative side, and total is 0. This type of are called ferrimagnetic. If 5 electrons are there, 3 are clockwise, 2 are anti-clockwise. 3 are clockwise, 2 are anti-clockwise. Then what happens? Net 1 will be more. Anyone. Hence, even though 5 electrons are there, only 1 electron show the magnetic momentum. Such type of compounds are called anti-ferrimagnetic. In one orbital, 2 electrons are there. One is clockwise, one is anti-clockwise. Automatically, it is diamagnetic. That is, overall, the magnetic compounds are classified into 5 types. Depend upon this phenomena. If all the electrons of the atom paired and filled up, 3D10, for example, 3D10 means what happens? 5 electrons are paired up like this. Here, clockwise or anti-clockwise, both are neutralizing. whatever the magnetic moment created by the parallel electrons can be cancelled by anti-parallel electrons. Total magnetic moment is 0. But if he is having the only 4 electrons in like this, if 4 are rotating clockwise, it is ferromagnetic compound, possess magnetic momentum. Example, iron and cobalt. But if the two are having clockwise, two are having anti-clockwise, net is 0. It is called ferrimagnetic. And out of 5, 3 are clockwise, 3 are anti-clockwise. It is called anti-ferrimagnetic. But here 3 are positive, these two are neutralized, only one will be there extra. It can create the magnetic moment. And it is equal to only 1 electron compound. Even though having the more electrons but showing the less magnetic momentum. It's called antiferric compound. Sometimes these are going to be supported by the Upender momentum, or sometimes pinching. They may be reduced this Upender momentum. Upender momentum may be enhanced because of Upender momentum, or sometimes this Upender momentum will be pinched by the Upender momentum. I will just very simple. Ferri, antiferri, only one or two. Manganese oxide, only one be there. Ferro means cobalt and iron. So now, quenching will be possible, and supporting will be possible, depend upon the atom. It will come in the 4D, 5D and lanthanide, not here. For in case of 3D series, only we are having the paramagnetic complex, diamagnetic complexes and ferromagnetic complexes, depending upon the only spin angular momentum, no orbital angular momentum. L is equal to 0 in all cases. Now, the orbital angular momentum, the magnetic momentum will be measured in the Bohr magnetons by using Guy balance. Now, according to that, paramagnetic substances means those substances which are placed in the external magnetic field, they are attracted strongly by the external magnetic field, their weight increases. Such type of compounds are called paramagnetic compound. Those compounds which have the unpaired electrons or shows the paramagnetic behavior. Example, except zinc plus 2 zinc, cadmium plus 2 cadmium, scandium plus 3, that is 0. If the d orbital having a 0, d3d 0 and 3d10 elements are the examples for this one. For example, cadmium plus 2, mercury plus 2, cadmium, zinc plus 2, copper plus, silver plus, rm plus. All these are diamagnetic. Scandium plus 3, yttrium plus 3, lanthanum plus 3, all are diamagnetic. Titanium plus 4, diamagnetic. Chromium plus 6, diamagnetic, because all 6 electrons are lost, no unpaired electron. All these are the diamagnetic. What are the paramagnetic compounds? The compound which have the unpaired electrons in its d block elements are in the valence system. For example, titanium chloride, TaCl3 plus 3, 3d1, it is paramagnetic. And copper plus 2, 3d9, one unpaired electron is there. Titanium plus 3, copper plus 2, both are having the same paramagnetic behavior. Because it is 3D, it is 3D. Only one electron is unpaired. Yes, 3D1 is there, 3D9 is there. 3D9 means what happens? 1, 2, 3, 4, 5, 6, 7, 8, 9. One unpaired electron. Ferrous, iron, Fe plus 2. 3D6. 3D6 means 4 unpaired electrons. 1, 2, 3, 4, 5, 6. These all 4 are parallel ferromagnetic. 3 are parallel, 1 is anti-parallel. It is ferrimagnetic. Antiferrimagnetic. Like that, ferromagnetic compound, ferrimagnetic compound, antiferrimagnetic compound, diamagnetic compound. Diamagnetic means all electrons are paired. No electron is unpaired. They are going to decrease the weight. They are repelled by the external magnetic field. The weight is decreases. That is, it is south one, north one magnetic fields. If you put a paramagnetic substance, the forces are going like this. Now the magnetic forces are going to passing through the substance. Due to that, it will be attracted by the stock field. Its weight increases, such as TiCl3, copper, etc. If it is diamagnetic compound, what happens? These are going to, the forces are going to repulse and they are not going to allow to pass. It is called diamagnetic. If these forces are strongly passing, means it is called ferromagnetic. That is more number of electrons with parallel spin. So this is about the magnetic momentum. What is the magnetic momentum? How to know the magnetic momentum? Now I am going to explain here. For the 3D series, you have to follow the root n into n plus 2 is the formula. Root n into n plus formula is equal to bar magneton, or 4s into s plus 1 root. Here s is equal to spin, n is equal to number of electrons, number of unpaired electrons. For example, I am over copper sulfate. What happens is 3D9. 3D9 means only one electron is there. Then 1 into 1 plus 2. 1 into 1 plus 2. How much? Root 2. So root 3, sorry. Root 3 is equal to 1.734 bar magnetons. This is the magnetic moment of copper sulfate. Directly, we can calculate. To experimentally, we have to calculate with this Guy balance. Guy balance is the one experimental one. Experiment to calculate this one. And next, now you can say that anyone can answer that. What is the magnetic moment of manganese sulfate? Answer immediately. Repeat. Next, any other one? Nickel chloride. Yeah, very good. 5.9 something, because 5 electrons. Nickel 3D8. 1, 2, 3, 4, 5, 6, 7, 8. Like this. And 1, 2, 3, 4, 5, 6, 7, 8. 2 electrons. 2.8 something. So this is about paramagnetic behavior and Spinelli formula. This formula is called Spinelli formula. But if you want to calculate the remaining, what are that? 4D and 4D and 3D, that formula is not useful. In that, you have to calculate with the one other formula, that is called mu is equal to G into root J into J plus 1. This is a formula. Write down formula to calculate the 4D, 5D and lanthanides and actinides, because their spin angular momentum as well as orbital angular momentum, both are going to combination of these two. Sometimes L will enhance the S value. Sometimes pinching of S value will be taken. It depends upon the nature, and hence it is given by J. J is equal to here. J is equal to L plus S2, L minus S. It is the one other formula. G is equal to 1 plus S into S plus 1. That is not required, but for understanding, first 1 plus S into S plus 1 minus L into L plus 1 divided by 2J into J plus 1. The G value. Very cumbersome experiment. More exercise required to calculate the magnetic momentum of D block elements other than the 3D series and lanthanides and actinides. This is the formula G. It is called J is called rotational constant. So G is called gyromagnetic ratio. So it is a different matter. We will discuss the spectroscopy, not here. So any doubts, any clarification regarding this and it is very much useful in the coordination compounds to calculate the magnetic momentum of any complex compound, etc. And if you are not having any doubts, I will go through the next topic. So next I am going to discuss the color properties. Color properties. Yeah. Okay. So listen to me, Nana. First of all, take any compound. Give any example. You. Just ferry and anti-ferry. Very simple. Just one or two are there. Not much. That is not affecting you in the entrance examination. I will tell you that tomorrow. Just MnO2 and something. Only one or two examples are there for ferry and anti-ferry. Need not to worry about that one. I can give tomorrow by seeing the examples. And anyone give any example, I will explain. Magnetic momentum. Anyone example? Mira event okati. Copper sulfate. Already explained. Copper sulfate. Okay. Any other one? మీరు చెప్తేనే చేస్తా మీకు. Yes, using spin value I will explain, but you have to give the one more. Sorry, I am going to take the one more example. Cobalt chloride, and I am going to take the ruthenium fluoride example. Listen to me. Copper sulfate, -2, it is +2. Copper +2 means copper is equal to 29, argon 4s1 3d10. After losing 2 electrons, copper +2 27. After argon 4s0 3d9. So how many electrons are there? And write down the electron configuration. 1 2 3 4 5 6 7 8 9 10 9 one electron. S is equal to +half. S is equal to +half. Okay. Now what is the formula? Mu is equal to what is the formula? Root 4s into s +1. 4 into half +1. What happens? 2 into 4, 8. 8 by 2 means 4. 2 2 ja 2 plus identa 2 into 1 plus 1. 2 by 2. ఎంత అవుతుందిరా అది? 4s into s plus 1. S is equal to half. Again calculate. 4 into s half. S plus 1. S into half plus 1. Tell me that how much it is? 2 into half. What is the 2 by 2 4. Calculate. 4 into half అంటే 4 by 2 into 1 by 2 plus 1. It is root 2 plus 1. 2 into 1 by 2 by 2. 2 into 1 by 2 by 2 అంటే plus 1. 4s plus 1 కదా. Is equal to 1 is equal to root 2 1.4 and take 1 root 3 it is equal to root 3 1.74 bar magnon. Similarly nickel chloride 3d8 4s0 2 means 2 electrons. How it is 2 electrons? See here 1 2 3 4 5 6 7 8 2 electrons. mu is equal to 4 into, sorry, 4 into, yes, s is equal to 1. 1 plus 1, 2, 4 to the 8, root 8. Root 8 is equal to 2.8 government and something. 4 1 plus 1 2, 4 to the 8, 4 to the 8, like that. And coming to the ruthenium fluoride, ruthenium given to iron group, 26 iron plus 18, 44. Ruthenium plus 3, ruthenium plus 3 means ruthenium group 46, 45, 5s0. How many electrons? 5 electrons. 1, 2, 3, 4, 5. 5 into half plus 5 plus 1. 5 by 2. Sorry. Yes. Sorry. I am going to explain like this. 4 into 5 by 2. 5 by 2 plus 1. 4 2 4 ja 8 5 ja 40. 40 by ఎంత అవుతుంది by 2. Do it calculation. We are going to get the 5.8 something. 25. Okay, like this. Any other? దానికన్నా n into n plus 2 better. N into n plus 2 is better. Number of unpaired electrons 1 plus 2 3 root 3 4 plus 2 5 4 20 root 4 root 5 root 20, like that. It will be very easy. S into s plus 1 కన్నా అది ఈజీ క్యాలిక్యులేషన్. ఐపీస్ వాళ్ళకన్నా ఈజీ చేయొచ్చు, ఎంపీస్ వాళ్ళు కొంచెం ఏదైనా చేస్తారు. ఎనీ అదర్ నానా? ఐ థింక్ 3 o'clock మీ వేరే క్లాస్ ఉంటుంది కదా. సో టుమారో కలర్ ప్రాపర్టీస్, catalytic properties, formation eligibility, and comparison between the 3D and 4D 5D elements followed by the F block, electron configuration F block, and same color properties, magnetic properties, oxygen states, lanthanide contraction, actinide contraction ఇది చెప్పుకుంటాము. ఇక మీరు చేయాల్సిన పని ఏంటంటే టిటానియం ట్రయాడ్, క్రోమియం ట్రయాడ్ అండ్ కాపర్ ట్రయాడ్, ఈ 3 ట్రయాడ్లు చదువుకొని బుక్లోకి వెళ్ళి ఏమైనా డౌట్స్ ఉంటే, క్లారిఫికేషన్ ఉంటే నాకు రేపటి క్లాస్లో అడగండి. దానివల్ల మనకు చాప్టర్ అయిపోతుంది, ఏ ఇబ్బంది లేకుండా అయిపోతుంది. మీరే యాక్టివ్గా ఉండాలి ఇక్కడ. మనం చెప్పుకోవాల్సింది చాలా తక్కువ ఉంది. ఇప్పుడు ఒక కాంప్లెక్స్ కాంపౌండ్ కలర్కే టైం తీసుకుంటుంది, మిగతా ఈజీగా అయిపోతాయి. వై కలర్ ప్రొడ్యూసెస్, హౌ కలర్ ప్రొడ్యూసెస్, హౌ టు ఐడెంటిఫై ద compounds which are colored, which are not colored, which are brilliant colors, which are pale colors, why they are pale colors, why they are brilliant colors, which are allowed transitions, which are not allowed transitions, what is the symmetry forbidden, what is the symmetry not forbidden, ఇవన్నీ మనం చెప్పుకుంటారు క్లాస్లో. అది ఒక్కటి అయిందంటే catalytic properties, complex compound formation, everything will be very easy. Within the 1 minute 2 minutes అయిపోతుంది. ఒక కలర్కి బాగా టైం తీసుకుంటుంది. ఇప్పుడు నేను చెప్పిన కలర్ ప్రాపర్టీస్ వింటే కోఆర్డినేషన్ కాంపౌండ్ చెప్పేటప్పుడు చాలా ఈజీ అయిపోతుంది. కనుక మీరు రేపు కలర్ ప్రాపర్టీస్ కొంచెం ఓపిక వినాలి. కలర్ ఎందుకు వస్తుంది, ఎప్పుడు వస్తుంది, ఏ కలర్ అబ్జర్వ్ చేసుకుంటే ఏ కలర్ ప్రొడ్యూస్ అవుతుంది, ఆ కలర్ రావడం గల కారణాలు ఏంటి, వై జింక్, cadmium, mercury do not having color, why copper plus do not have color, copper plus to have the color, why D block elements have the different colors, why lanthanides having the same color, all lanthanide elements. For example, europium plus 3, its color will not be changed by the changing the ligand atmosphere. But if you take the iron plus 3 with water other color, with nitro ligand other color, cyanide ligand other color, if you change the ligand, immediately color will be changed. But in case of lanthanides, if you take the lanthanum as europium for example, whatever the color is there, the same color will be there for always with any ligand. If you change the ligand, no color will be changed. But in the case of D block elements, color will be changed by the changing ligand. So why both are colored? Both are colored. For example, samarium is there. Samarium color is red, for example. Samarium test with red color. The red color will be red color with ligand changing. But ferric iron is blue color, brown color with the hydroxide. But it is going to change with the, if you change the ligand, color will be changed. And some more, potassium dichromate has the very strong orange red color. KMnO4 has the purple color, bright colors. But ferrous sulfate, manganese sulfate, flesh color like this flesh color, manganese sulfate, very pale colors. Copper sulfate, very pale blue color. Why these are having the pale blue color? Why they are the strong color? What type of colors they are producing? Why they are producing colors? Like that, what is the difference between these two? And when the color collapse, for example, copper sulfate is there. If you copper sulfate with water light blue, with ammonia thick blue, with chloride green color, if you change the ligands, color will be changed. For example, copper sulfate in the beaker, blue color. If you add the ammonia, dark blue color. If you add the HCl, green color. Again add the water, light blue color. Again add the ammonia, dark blue color. Again add the HCl, green color. Within the fraction of time, color changes and color will be old color will be collapsed and new color will become. But this is not possible in the lanthanides. Whatever the ligand, color will be same. Why their color is not changing? Why here color changing? What is spectral properties, etc., will be discussed in the next class. Very interesting one will be there. And at the same time, all of you go through the lanthanide magnetic properties. I won't repeat it. I will give you just a graph. How the starting from lanthanum, europium and cerium, ఇట్లా పెరుగుతుంది గ్రాఫ్. ఆ గ్రాఫ్ ఎట్లా వస్తుందో చూసి మీరు ఇప్పుడు చెప్పిన పాయింట్ కవర్ చేసుకొని అది చదువుకోవాలి. లాంథనైడ్లలో యూరోపియంలో 0 ఉంటుంది, సెరియం హాల్మియం డిస్పోజియంలో చాలా ఎక్కువ ఉంటుంది. కానీ అన్పెయిడ్ ఎలక్ట్రాన్స్ యూరోపియంలోనే చాలా ఎక్కువ ఉంటాయి. దానికి కారణం ఏంటంటే పించింగ్ ఆఫ్ ఆర్బిటల్ యాంగులర్ మొమెంటం బై థిన్ యాంగులర్ మొమెంటం బై ఆర్బిటల్ యాంగులర్ మొమెంటం. ఈ విషయాలు మీరు ఒకటి చదువుకోండి. రేపు క్లాస్కి వచ్చేసరికి మీరు కొంచెం అలర్ట్గా ఉంటే tomorrow and day after tomorrow I will complete the D block elements and I will go the metal carbonyls. After that, at the end of the topic, I will continue the carbonyls boranes. So once Ramesh sir, are you in the line, sir? Utana sir, Narayana? Okay. Can I close the topic class now?
Sir.
సార్ ఇప్పుడు
సార్ ఏం చేద్దాము
అది చేద్దాము. ఇంకొకటి ఏంటంటే
సార్
నేను చెప్దాం అనుకున్నాను, ఆ పాత పేపర్ చూసారా సార్?
ఏది సార్?
లాస్ట్ ప్రీవియస్ క్వశ్చన్ పేపర్.
ఓకే.
అది పట్టుకుంటే మొన్న పోయినసారి కార్బోనేట్స్ ఏం ఎక్కువ వచ్చినాయి, మెటల్ కార్బోనేట్స్ ఎక్కువ వచ్చాయి, పూర్తి చెప్పచ్చు.
అది సిపికెట్ ది దొరకట్లేదు సార్. ఓయిది మాత్రం అంటే రెండు దొరికాయి. సిపికెట్ అది ఇక్కడ మిస్ప్లేస్.
లైబ్రరీస్ చెప్పండి సార్, లైబ్రరీ దొరకబడతారు వాళ్ళు. మన లైబ్రరీ, మా లైబ్రరీకి చెప్తాను, అది దొరికింది అనుకోండి.
సరే ట్రై చేద్దాం సార్.
చూడండి, నేను మా లైబ్రరీ కూడా చెప్తాను.
ఓకే సార్, ట్రై చేద్దాం.
ఒక 2 days లో 2 classes లో ఇది అయిపోతుంది సార్. నెక్స్ట్ మెటల్ కార్బోనేట్, ఆఫ్టర్ కార్బోనేట్
కొంచెం స్పీడ్గానే చేయండి సార్, ఇంకా కొంచెం దగ్గరికి వస్తుంది. ఎగ్జామ్ పోస్ట్పోన్ అయ్యేటట్టు కూడా లేదు ఇంకా.
ఇక మళ్ళీ నేను చెప్పింది వాళ్ళు చదవాల్సిన అవసరం లేకుండా చెప్తున్నాను సార్. నోకాల
అదే అదే చూస్తున్నాం, డీటెయిల్ గా ఉంది పిల్లలకి. థ్యాంక్ యూ సార్.
చెప్దాం అనుకున్నా 3 o'clock మేడం క్లాస్ ఉంది కదా సార్, అందుకని క్లోజ్ చేస్తాను.
ఓకే సార్, మా ఎట్లా 3కి వేరే ఉంది సార్, మన చంద్రమౌళి సార్ ఉన్నది.
అదే సరే.
ఓకే సార్, థ్యాంక్ యూ సార్, థ్యాంక్ యూ వెరీ మచ్.